All right, welcome everyone to the inaugural talk for the Pulses, Q-Trits, and Quantum Simulations workshop here at the IQuS. We are happy to have a wonderful overview talk given to us by Yaniv Rosen from Livermore National Lab, who's going to give us sort of a short, detailed course on superconducting qubits and how to use quantum computing using them, so that we can both get sort of the low-level view of how we do this pulse type control, and then eventually tie it back to our high-level algorithms later in this workshop. Anyway, Yaniv, please take it away.
Thank you very much. So my name is Yaniv Rosen. I'm from Lawrence Livermore National Lab, and at Lawrence Livermore, we're very interested in quantum simulations. So a lot of people tell you that the reason you want to do quantum simulations is so that you can recover lost Bitcoin passwords. But in the 1980s, Feynman coined the idea of actually using quantum simulations, quantum type computers, to do computations for quantum mechanics. And so at Livermore, we do a lot of quantum mechanics, and that's why we have a lot of HPC, and that's why we're always looking at the next generation of computing, and quantum computing is one of them. So we're very interested in quantum computing, and to understand it, first we should talk a little bit about regular computing. So in regular computing, you have zeros and ones, as we all know, and they encode in different methods. So we have zeros and ones that are magnetic states that point left or right. We have transistor switching, optical gradients. You need some kind of physical mechanism that can encode a 0 or a 1. And quantum computers are the same. We have zeros and ones, except that in a quantum computer, we can have a superposition of 0 and 1. So this is really just a state, which is a 50-50 probability of being either in the 0 or the 1, except it encodes this additional piece of information. And we like to represent this additional piece of information with a phase, with a complex number. So we can be in 0 plus 1, we can be in 0 minus 1, but then we can also be in 0 plus I1 or minus I1. And we can have any arbitrary phase, and that's just an additional piece of information that you need to keep track of when you have a quantum computer, a quantum bit. If you have 2 quantum bits, it gets a little bit more complicated. You need to keep track of 3, or actually in this case, 4 different pieces of information. If you have 4 qubits, it takes 16 different pieces of information that you have to keep track of. And with just 6 qubits, it's 64. So you have this exponential increase in the amount of information that you have to keep track of when you have multiple qubits. Each one of these variables is a different variable that you can control, that you can measure, that you can apply operations to. And this is both the reason why quantum mechanics is difficult to simulate on classical computers, and the reason why quantum computers are perfect for simulating quantum mechanical information. So how does this actually work? How do we do this? So there are many different types of quantum computers out there. These are just a few, and a few of the companies that are looking into the different technologies. And we still don't know which one is going to win out. There's a lot of investment in superconducting systems. Them and ion traps are probably the most mature, but there's a lot of other technologies which are slowly coming up and might actually outperform the other more conventional ones. So no one really knows which horse is going to win, but it's important to research them. And more than just computing technologies, these technologies are giving us access to quantum phenomena in a way that we haven't had before. And so even if one of them wins the quantum computing race, the other ones are still going to give us quantum sensors. They're going to give us different ways of looking at the world, at quantum mechanics, that is very interesting. For us at Livermore, we've started investing in superconducting quantum computing, and so that's what I wanted to talk about today. How does a superconducting quantum computer work? What is the 0 and 1? So in classical computing, we understand about the magnetism and the optical gradients, but a lot of people start to get lost when we start talking about circuits. And so I wanted to give an overview of how that works. So I'm a physicist, and I'm an experimental physicist, and so I don't go very much in theory, and the only thing I actually know how to solve are springs. So we're going to start with a simple spring. But mechanical systems are messy, they're difficult to work with, and so we want to do an LC circuit, an electrical spring. So that means just sticking an inductor and a capacitor together, oscillating between electric and magnetic fields. Now, we can't just rely on these simple equations of motion. We actually have to do a little bit of quantum mechanics, so that's when it starts getting complicated. But really, the only thing that matters in this equation is this last bit over here. The En, the energy is quantized. The energy increases in steps of h bar omega. What does a spring look like? So it's really easy to make an electrical circuit of a spring. This is a simulation of one of these systems. You just take a block of sapphire, you stick a thin piece of superconductor on it, and you look at its eigenmodes. And it turns out that you can have a λ/2 resonator. This is electric fields, so you get electric field antinodes at the edges and then large current in the middle. And this is a harmonic oscillator. If you take this system, you cool it down to very low temperatures, you put very little energy inside it, you can fill it up with very few photons. This is the simplest harmonic oscillator that we can make. And there are different versions of doing this. There's different circuit elements. And depending on what we want to do, we can play with different ones. We can use capacitors. So if you have ever looked at Google's papers, their qubits are these X's. That X is just a capacitor. It has some capacitance to ground. If you look at, if you see something that looks like this, interdigitated electrodes, those are capacitors. And then meanders are inductors. You just take a long wire, and that is an inductor. We also have to add a magical component for superconductivity, which we'll talk about a little later, but that's a Josephson junction. So a Josephson junction is just a tunnel junction. It's a metallic layer or superconducting layer, a dielectric and a superconducting layer. It looks a lot like a capacitor, but it throttles the number of electrons going through. And so the equations are actually more like an inductor. And I'll get into that a little bit in a bit. But to begin with, let's just start with superconducting resonators. So we can write down a circuit, a simple LC circuit. We add a resistor because all circuits have to have resistors, and then we have to couple to the outside world. So we either couple capacitively or inductively. This is one of the simpler ways of representing one of these circuits. We have the frequency for that system. It's 1/√LC. It has quality factors, and we can write down a simple equation of motion for it. We can also probe it. So this is transmission. So over here, we're looking at transmission as a function of frequency. And this oscillator looks like a filter. It looks like either a band pass or, in this case, a band stop filter. So you load it up with energy right when you're hitting it with the resonant frequency. There's a few important parts, two main important parts for the circuit. One is the full width half max, how much loss, what is how accurately can you get the frequency for the circuit, and then the resonant frequency for it. I wanted to take a second and just talk about the loss, because this is something that I think when Kyle was talking about bridges, this is something that's very important to us in the experimental world, but in the theory world, most things are ideal. So I wanted to talk about a few of the measures of the loss. So one of the things that's very important for us is the quality factor. How deep does this go? What is the width here? And if you hit it with a hammer, how long does the system ring? this quality factor tells us how much power loss we have in the system. And ideally, we would like to have zero power loss. Ideally, we would like infinite quality factors, but that's never the case. So we can go and explore the quality factor as a function of different parameters. One of those parameters is the voltage, the number of photons that you put in the resonator. It turns out that if you put many, many photons into the resonator, you start seeing a decrease in the loss. So over here, this graph shows the power loss, 1 over Q, as a function of the voltage or number of photons. And we see kind of two regimes. When we're in the very small photon, very small voltage regime, everything looks like a straight line. Straight line means a resistance. It means that you just have this linear source of loss. You're just losing photons depending on how much energy. If you put 10 photons inside, you'll lose 1 a second. If you put 100 photons inside, you lose 10 a second. That's just regular classical physics. But this section over here, you actually have a nonlinear loss. And that's telling us something actually very important. It's telling us that the sources of loss are finite. They can only accept a certain amount of energy. We model this with a 2-level system model. So if you imagine that you have a qubit that's connected to a whole bunch of other qubits. If we start at the very low energy limit, everything is in the ground state. We start at very low temperatures. Now we stick a photon in our qubit, but that photon gets lost. Well, if we're in the very low energy limit, then that photon will decay and will be ready to accept another photon, will be ready to just get more loss. So we're in the linear regime because every time you stick a photon in the qubit, it goes to the 2-level systems and then just gets lost. But if you start exciting it with many photons, you put a photon in, it excites a 2-level system. You put another photon in, it excites another 2-level system. If you try to put a 3rd photon in, it won't have room. It won't be able to excite a 2-level system. You've saturated them. When you put too many photons in your qubit, in your resonator, you saturate the 2-level systems, and they can no longer accept any more energy. And so you actually have a reduction in power loss when you go to higher energies. This is a signature. This is telling us that these are actually 2-level systems. These are qubits in our materials that we're using. And it's actually a great source of consternation that we're trying to make this perfect qubit, but the dielectrics that we use already have an infinite number of them. There's already a bunch of qubits in nature that are interacting with our qubit and preventing us from having high coherence. And we can actually see these. So you can tune your qubit frequency using various parameters. You can flux tune your qubit, or you can actually tune these 2-level systems by putting strain on your system, voltage on your system. And you can see these features, which are nature's qubits in the materials interfering with your qubit, reducing your T1 times and just causing loss and decoherence. So this is something that we're working a lot on solving. But let's get back to our superconducting resonator. So we have a perfectly harmonic resonator. We have energy goes in steps of omega, h bar omega. And we can write down the equations for this. So we can look at the current as a function of time, or the differential equation for current. It's just a 2nd order PDE. We like using flux and charge instead of current and voltage, so I'll switch to that. We can write down the potential energy, we can write down the kinetic energy, and we just have a parabolic potential. So if we look at the potential energy of a harmonic oscillator as a function of the flux, so the flux being the magnetic field times area through your inductor, you just get a parabolic potential. and your energy levels are equally spaced. So I created this LC circuit. I'm going to apply an electric field to this LC circuit. The electric field is going to be at the frequency of the circuit. So cosine omega t, where the omega is the same omega as my energy. And if I start completely in the ground state, which I can do, I just start at 0 temperature, I'm going to start adding photons. So I start with 0 photons, I add 1 photon, but now I have a problem because I know how many photons there are, but I don't know the phase of the system. And so I have an equal probability of being in phase or out of phase. I can do constructive interference or destructive interference. And I can't know which one I'm doing. And actually, when I keep applying the electric field, this cosine omega t, I'm in a superposition of both adding photons and subtracting photons. So if I keep going, if I keep applying this electric field, I'm increasing the photon number, but I'm also decreasing it at the same time. And this makes calculations very difficult. This is called the coherent state. We go into a Poissonian distribution of the photon states. So this is bad. I can't do computations on this. This is analog and continuous. And so I need to figure out a way to fix this. So the way we fix it is instead of using an inductor, we use a Josephson junction. So how do I think about a Josephson junction? So Josephson junction is, like I was saying, a tunnel barrier where I throttle the number of electrons that can jump from one side of the Josephson junction to the other side of the Josephson junction. The energy stored in it is actually kinetic energy. And so the more current I try to shove through, the faster the electrons have to go through. And the equations of motion are very similar to an inductor. But they're slightly nonlinear. And so my potential is actually a sinusoid. So when I write down my PDE, I have the sine theta, or sine phi. And sine phi is slightly nonlinear. So I get this phi to the third, which makes my potential just slightly different than parabolic. Now, there's a really nice analogy to this, and that's pendulums. It turns out that a pendulum has exactly the same equations of motion as a Josephson junction. So next time you're playing with your kids on a swing, you can go and think about Josephson junctions and do all the math. The Wikipedia has these great graphics on pendulums, and the key is that the frequency of oscillation changes depending on the amplitude of oscillation. So if you have very small amplitudes, then you go fairly fast. But if you have very large amplitudes of oscillation, it can take a very long time to do a full period. And this is exactly what we're making use of when we are using these Josephson junctions. If you have few photons in the system, you have a fairly large frequency. But if you have many photons in the system, your frequency gets smaller and smaller. And so we add this component to the Hamiltonian that's dependent on the number of photons. So now, if I apply my electric field, I apply cosine omega t. Omega, the frequency of the Hamiltonian, or the frequency in the Hamiltonian, is only omega when n is 0. If n equals 2, I have this this change. So when n is 0 or 1, the energy difference is omega, but otherwise it's different. And so now if I go and apply my electric field, I'm going to oscillate between 0 and 1. And I'll do this controllably. So this is how we control a qubit in a superconducting system. Now, one thing to note, which I think is very deep, but I haven't figured out why yet. If I take this cosine omega t and I change it to a sine omega t, that's how I perform sigma y operations instead of sigma x operations. So I just change the phase of the pulse that I'm applying and that changes where on the block sphere I'm rotating. And we can do this and we can see Rabi oscillations. So this is just a measurement that I took on our system. Okay, so I have my qubit. It's a capacitor with a Josephson junction. This is a 3D transmon system. I can look at the electric fields. So these are equal electric field maps. And my qubit is right over there on the little sapphire piece. My qubit is capacitively coupled to a readout resonator. There's a few reasons for this. One of them is to block the environment from affecting my qubit, but one of them is also so that I can actually read out my qubit without completely destroying the state. So how does this work? My qubit so there's some capacitance coupling. When my readout resonator is oscillating, it has some component that's interacting with the qubit. So it's putting current over that Josephson junction, which means that when my Josephson junction moves, I get a slight shift in frequency. And so this is what it looks like when I look at my readout resonator for different qubit states. So this is transmission as a function of frequency. If my qubit is in the 0 state, if I have no photons in my qubit, then I have the rightmost curve. If I have 1 photon in my qubit, I've changed the period of oscillation of the Josephson junction. I've changed its properties, so its inductance is effectively changing a bit, and then my readout resonator changes. So my goal is to when I measure a qubit, my goal is to figure out what is the frequency of the readout resonator. And the way we usually only can choose one frequency to measure it at. So performing one of the big curves can take minutes. And we don't want to spend minutes doing a measurement on the system just to figure out what the qubit is. And so we have to choose the ideal frequency. If we look at the transmission of a superconducting resonator as a function of frequency, we get either a peak or a dip, a band pass or band stop filter. If we look at the phase of the returned wave, the IQ graph, it looks like a circle. So the way to read this graph, we send in a pulse, a cosine omega t pulse, to probe the resonance frequency. And then we have a pulse that comes back, which is shifted a bit in phase and a bit in amplitude. And it's shifted, so 0, 0 would be 0 amplitude. 1 over here would be amplitude but no phase shift. And any changes in the vertical give us a phase shift. If I look at these three frequencies, I see phase shifts in different ways from the returned pulse. If I have a qubit that's in the 0 state compared to a qubit that's in the 1 state, my resonance frequency shifts, and I get different results if I probe at the same frequency. So if I choose a frequency, for example, here, where they both overlap, where the amplitude is the same, if I look on the IQ graph, if I look at the amplitude and phase of the returned probe, I get a point that's shifted, not in amplitude, but the phase changes by a significant amount. So if you're talking to experimentalists and they're talking about readout, they're talking about an IQ graph and trying to distinguish readout, this is what they're doing. They're probing the system with a pulse, and then they get a pulse back. They're looking at the phase shift from that pulse. They're looking at this IQ graph, and if their qubit is in the ground state, they get a bunch of measurements in one position. If their qubit is in the excited state, they get a bunch of measurements in a different position, and they're trying to distinguish them. If these blobs are too close together, you won't be able to distinguish them. If they're far enough apart, then you will. And this also is how you do single shot fidelity. You do a single shot, and you hope that the blobs are well separated so that you can determine where that shot hit. Okay, so that was a lot of very introductory physics about how qubit works. Are there any questions or comments or? Yeah.
So, I'm not really understand. You said that if you put input different frequency, you can get different results.
Yeah.
So for the graph, in order to make that plot, you need to fix the frequency, or you can change the input frequency.
Oh, so we can probe it we can probe the readout resonator at different frequencies. So if you're probing exactly on resonance, then you will see a maximum amplitude change. But your phase shouldn't change at all. It should be exactly the same phase that you got before. If you are off resonance, then you'll see a change in the phase of the wave that you get back. Does that make sense? Or here, I can.
I just try to relate those measurement plot with the plot in your previous slide.
Okay. So this is the actual equation of the transmission. It had you can look at the magnitude of this equation, and you can look at the phase, or the real part and imaginary part of this equation here. If you look at the magnitude, then it looks like a dip or a peak if you get rid of this one. If you look at the real part and the imaginary part, that makes a circle. And depending on your frequency that you choose, you get a different position on that circle, or you get a different position in the amplitude. Okay. Uh-oh. Okay. So now, upload. Oh. Okay. So now I wanted to talk very briefly on just how we notate the different systems. And this is because I've interacted with a lot of mathematicians and computer scientists who get very confused when we talk about bracket notation. And so for us, we like to represent the states in bracket notation, but really we're talking about vectors or even matrix representations. And so it's always useful to see what it looks like in the different representations, especially when you're trying to expand them, tensor everything together, and take it apart. So a 0 is really simple. It just means that you're on the top of the block sphere. A 1 means you're at the bottom of the block sphere. And in vector representation, it's just 1, 0 versus 0, 1. One thing that we should also mention is that if you're in the 1 state, quantum computing will tend to go towards the 0 state. It will tend to, everything, your environment is usually at 0 temperature, and your qubits thermalize with the environment, although slowly. And that means they try to reach the state of the environment. So if you're at high temperature, your qubit will try to go to 0 plus 1, or both 0 and 1. If you're at 0 temperature, it'll try to go to 0. And that means that over time, you will lose if you start in the 1 state, you'll lose it and you'll go towards the 0. The other phenomena that happens is we tend to scramble the quantum information. So you can start in the 0 plus 1 state, but eventually you're going to lose that information and you're going to go into a mixed state. We represent these with different density matrices. So I don't know if it's useful to go into density matrix representation, but the reason you use density matrices is if you don't have all of your quantum information, if you started going into a mixed state. So a pure quantum state is if you have useful quantum information between the 0 and the 1 state. So you retain this plus sign or minus sign or J information. You know where you are on the equator. But if you have, you can actually reach a state where you have a completely random point flip, where you don't know what your quantum information is. The way we like to talk about it is with density matrices. And what happens is our density matrix loses its off-diagonal components. It loses the quantum information. So our diagonal here tells us the probabilities of the system, and the diagonals in both cases are the same, but the off-diagonals are a representation of the quantum information of our system. And there we completely lose our information. What's the difference between a mixed state and a pure quantum state? Well, one example is the pi/2 rotation. So if you are in a 0 plus 1 state, you can perform a pi/2 and get to a different quantum state. But if you're in a mixed state, you can't perform any unitary operations. You can't do any rotations around the Bloch sphere to get it out of the state. You have to perform a non-unitary operation to get it out of the state. You have to either wait for it to decay or you have to measure it. You have to destroy your quantum state to actually start over again and get useful things. And then I should mention that there are ways of actually making these states more robust. So you don't have to go and wait for an error to occur. If an error does occur, there are different ways of correcting for them. So there are error correction algorithms that can be used to stabilize these systems. One thing that's worth mentioning is that there are concepts called physical qubits versus logical qubits. A physical qubit is the qubit that we built, and we show you over here. The circuit elements is just a capacitor and a Josephson junction. That's a physical qubit. They're lossy, they don't work well, but they're what we have. A logical qubit is an ideal qubit where you can perform operations on it and it won't lose the quantum information. The way to create logical qubits is by using many physical qubits in some kind of error correction code to stabilize the logical qubit. So one of these could make up one logical qubit that has much more robust characteristics than a physical qubit. And then if you put 2 qubits together, the system becomes more complicated. So if you have 2 qubits, like I was saying before, you have 4 pieces of information that you have to keep track of. Our density matrices start getting very complicated, and we start storing more quantum information in the system. And then we can talk about gates. So different gates will perform different operations on the system. And here we start to add more notation. So there are matrix notations for gates. There's also different symbols, and these symbols can be used to make up a quantum circuit. So if you put all of the symbols together, and there are many different symbols, both for 2 qubit gates and 1 qubit gates, you can put a quantum circuit together, which allows you to actually perform mapped different quantum operations. All of this together is how we do digital universal quantum logic. But digital universal quantum logic is, I would say, a classical way of thinking of things. So in the past, what a lot of people have tried to do is impose classical computation paradigms onto quantum computing. And so if this is a Google qubit, a lot of people, or quantum processor unit, a lot of people like to draw a square around the system and say, this is one qubit. They like to talk about the 0 and 1 state and say, this is 0 and 1. This is this is what a qubit looks like. But really, they're a lot more complicated than this. We have the 2 state and the 3 state. And it used to be that when people accidentally went to the 2 state, this would be quantum state leakage. If you accidentally went and excited a qubit that you didn't mean to excite, then they call that crosstalk. But there are other ways of thinking about this. If you take the entire system as a whole, if you treat the system as a single Hamiltonian, then you can actually include all of it in your computation. And then there's ways to correct for different effects. So if you actually, there's different ways of making the circuits so that you can control different modes. There's different ways of going to the higher levels, which Robbie was talking about, using QDITs to actually control the higher levels instead of just ignoring them as quantum state leakage.
Okay.
And this is a very early experiment where we wanted to show that we could perform QDIT operations in a more robust way than what people had thought about previously. And we wanted to show that we could do a 0-2 swap. So doing a 0-2 swap gate is a little bit more complicated than thinking in a 0-1 state. If you're doing 0-1, that is very easy. You can just apply a cosine omega t pulse and it'll Rabi flop you. If you want to do a 0-2, you have to do something a little bit more complicated. So this is the pulse that we derived. It requires more HPC, more classical compute to figure out, but we have a lot of classical computation that we can actually throw at the system and perform these calculations. So we derived this pulse for using optimal control, and we measured our QDIT system after this pulse at different times. So if we start in the 0 state, we can controllably move it to the 2. If we start in the 1 state, we can stay in the 1. If we start in the 2 state, we can controllably switch it so that the 0 state is most probabilistic. It is interesting that we see these little fluctuations. So this pulse has other features in it that we haven't, that are real, that appear both in the data and in the numerics, but they're unintentional. So we're not exactly sure why, but it's an interesting thing that either could be optimized or could be used somehow. But this is also useful for other calculations. So this over here is an early example of doing quantum simulation, which we worked on with Kyle, where we assigned different, the spin states of 2 neutrons to different levels of a QDIT. So we had the spin up, spin down, spin up, down, 2 different levels of the QDIT, and then we had a neutron-neutron interaction, which we implemented using optimal control. So we created one gate that could that emulated a Trotter step for a neutron scattering problem. This over here is the gate. We applied it and we could see oscillations. So these oscillations are the neutrons interacting with each other. So it's possible to use these bigger systems to actually emulate how the other quantum systems work. So with that, thank you very much for your attention. I hope that helps describe a little bit about how experimental superconducting systems work, what it is to have a 0 and 1 and 2 and 3, and how we can use them. So thank you very much.
All right, Yaniv, thank you very much for that great introduction to sort of low-level physics of how superconducting quantum computing works. And that was very, very enlightening, interesting. Thank you. I guess now we're going to open this up to questions both to the floor and to people online. Is somebody able to watch online for us? All right, excellent. So then I guess, and so we see online, so we'll start at the floor. Does anyone have anything to ask Yaniv or any sort of curiosity or comment?
Question just on the last part. So how does the fidelity scale as it, for instance, transitions from say 0 to the upper level versus 0 to the mid? Is there a systematic degradation or is it flat?
Yeah, so there are more sources of noise as you go to higher levels of the qubit, especially for a transmon qubit. There's the reason people chose transmons. Transmon is a special regime where you reduce the charge noise, but it turns out that you get more charge noise as you go to higher levels. There are also weird effects where you start interfering with the readout circuit. Usually your readout circuit is at higher energy, but if you have 2, 3 photons in your qubit, then you can start seeing degeneracies. The 0-3 transition can be the same as a higher energy readout transition. And so you can start, you do start getting effects.
Thanks.
So when you are dealing with a qubit system, these systems are characterized in part by the T1 time, right? So that will tell you more or less how much time you have to execute a quantum circuit before you are measuring noise.
Yeah.
What would be, I mean, when you are dealing with, let's say, just the qubits, now you have 3 states, so I guess there's going to be a different number, T, whatever you call it, that characterizes the case from the second excited state.
Yes.
How does that compare to the first? I mean, how much shorter is your time to perform your quantum circuit?
So it should scale as square root n. So you have
And being the number of the state.
the number of the state, number of photons. We see more or less that kind of scaling. There are a few deviations, but yeah.
Thanks for the nice talk. How do you think about quantum error correction for qubits or qubit systems?
So that's a very good question. I'm not sure I have that much of an answer for it. Yeah. So it is possible to map higher level systems onto regular quantum circuits. So a 4-level system is the same as 2 qubits. And so there are ways to map the circuits onto quantum error correction, but I suspect it's a lot more complicated than that because you have to access. So a lot of times with the error correction schemes, and there's different schemes, but what they like to do is have data qubits and ancilla qubits. So if you try to do something more complicated where your data qubit has 2 qubits encoded inside it, then that is going to complicate their correction schemes, but it's not something I'm well versed in.
Seems like an interesting problem, actually.
Yeah.
Maybe I have also just a very easy question. So you talked a lot about driving transitions in single qubit. Can you say just a little bit about like 2 qubit gates and how you couple qubits together?
Yes. So the main way, and unfortunately I don't have slides on this, but the main way you would couple two qubits together is by using a capacitance between them. So circuits. So you can couple them with a capacitor. So these elements are your basic building blocks, and you can use different combinations to couple the qubits together. Oh, that's interesting. Sorry for people on the Zoom. I don't know why it's doing that. But that's really weird. Okay. Yeah, so you can use, oh, thank you. Usually the simplest method is to use capacitances between them. If you use a capacitance, then that creates a dipole-dipole coupling. So sigma x, sigma x. A lot of people will then add a few Josephson junctions, and that gives you tunability. So you can turn the coupling on and turn it off. So you can have dipole-dipole coupling when you want, and then turn it off when you don't. That does add more control lines. It does add complexity to the circuit, which always adds complexity to the experiment.
In like slide 71 or 72, you showed like a bunch of different circuits, and yeah, this one. So in the bottom, those circuits are like swap and CZ, right?
Yeah.
So you just wrote them because like they're not equally hard, are they? Is this from my intuition, swap should be harder than a CZ? Is that true or not?
Actually, well, so ISwap is not too hard.
I see.
Regular swap, I think, is a little bit harder, but you can do ISwap, and ISwap is easier than a CZ if you can tune your parameters well. Yeah.
Do you have any questions online? Okay, well then let's thank Yaniv again for his wonderful talk.